Hello, this presentation will discuss a different view of how transformations act under composition. It's taken from section 2.2.7 in the book. So far, when we viewed composing transformations, we've always viewed the transformations as acting on an object and moving around in space. So for instance, if we formed a composition of a rotation and a translation, and we applied that to an object, we intuitively think of the object first being translated and then being rotated. For instance, the way we made the Earth rotate around the Sun in the solar system. And this, of course, means that the intuitive picture of how objects are being transformed applies the transformations in the reverse order they're written in the composition. We start with the one on the right first, and then work our way to the one on the left. Likewise, in a computer program, we start with the last line that applied a transformation in the computer program and work our way back up. And that's what guides our intuition about how transformations transform objects. But there's another way to view this. We can also think of transformations as transforming coordinate systems. So we can think of a local coordinate system that's getting moved around, and then at the end we draw an object based on the current local coordinate system. In this viewpoint, we actually view the transformations as acting from left to right instead of right to left. This is best illustrated with an example, so I'll just start on that now. The example is going to be based on an earlier video, also from an earlier section, so you can also see section 2.2.6, where the previous work was done. So in this situation, in this earlier example, we had a F that was translated and rotated. And let me draw the axes first. So the x-axis is here, the y-axis is here. We've got a F sitting in the standard position at the origin, and we transformed this by the following kind of picture. There was a distance L, angle theta from the x-axis. We then made a right angle turn. We went distance R, and then the base of the F was sitting right there. And so we actually did this blue F up here. Let me draw it black again here. This transformed F up here. This was transformed by the operation R theta, composed with T sub L0, composed with T sub 0 R plus 1, and then we applied that to F. So we took this whole thing and we applied it to the F shape, and it took the F as drawn at the origin here and would render it here. We had another F sitting at the bottom, but we're not going to consider this in today's lecture. And so this is an example of where the way we think of this is we think of this as being T0 R plus 1 of F. That moves the T up. We then take T L0 of that. That moves the F over, and then we take R theta of that, and that takes the F and moves it up to this position here where it's rendered. So that's how we've always thought about it in the past. Now I'd like to say that we can also think about this as transforming coordinate systems. So I'll just draw that on the other side of the board here. Make a little room, shorten this down. So let's draw this again. Here's the x-axis. Here's the y-axis. And what we're going to do is we're going to think about starting with a local coordinate system, and we're going to be transforming it according to these transformations. So we start off with the local coordinate system is just the standard one. So here's axis, I'll call it x superscript 0, and y superscript 0. So So x0, y0 form a local coordinate system in the sense of they're the usual coordinate system, and they're just defining the x-axis and the y-axis of the coordinate system. Now, let's try a different color here. Suppose I apply the rotate r theta. So that's going to give me coordinate systems, local coordinate system x1, y1, which is the rotated version of x0, y0. So that's here's like x1, y1. We think of the rotation, and we're going to apply it first, starting at the left, as rotating the coordinate system by angle theta. Now we're going to look at r sub theta composed with t L0, and that's going to define a new coordinate system, which I'll call x2, y2. I've switched to a new color, orange. Hopefully you can see this on your video. And what this does is the translation of L0 happens in the new local coordinate system. So here's x1, y1 as the current coordinate system. So we're going to translate distance L0 out here, and our new coordinate system sits here. So he'll be x2, y2, and it's rooted no longer at the original origin. This is the origin for the new coordinate system. So this is a origin for coordinate system x2, y2 is right here. And the direction of the two axes is given as drawn on the board here, right? And so that gives us the third coordinate system. We started off with local coordinate system x0, y0, then we have x1, y1, and finally we've got x2, y2. So, run out of room on the bottom of the board, I'll write it here, I guess. So now we do the third coordinate system. We look at r theta composed with t L0 composed with t 0 r plus 1. And for this we go distance r plus 1 in the current coordinate system, the x2, y2 coordinate system. And here is the new coordinate system for x3, y3. And so we get a local coordinate system, x3, y3. And this is the origin for x3, y3. And so now there's this coordinate system. We've moved it 3 times. We started here, then here, then here, and now up here. Each time applying the operations going from left to right. We rotated the coordinates, we translated them in the new coordinate system out, and we then translated again in the current coordinate system out to distance 0, r plus 1. And now we draw the F. When we draw the F, it gets drawn right here on top of the current. It's directly on top of the origin. I placed it off a little bit just so you could see things. When we draw the F, it finally gets drawn using the current coordinate system. So in this way, we've been able to rethink the way we view transformations. Instead of transformations acting right to left and moving the F around, the transformations act from left to right, and they move little coordinate systems around. And in the end, the F gets drawn in its position on the final coordinate system. So it gives a different way to think about this. This can be confusing because it's hard to switch modes back and forth. A lot of times it's more useful to think about this new way when we're doing things like the view matrix. So for instance, if you looked at the solar system code, there's code there for positioning the viewpoint at a certain azimuth above the solar system. And if you look at the code, what's going on there is that the solar system, in the old way of thinking about it, the solar system was being tilted and then pushed away from the viewer, pushed out the negative z-axis, with the viewer looking down the negative z-axis. In the new way of thinking about it, we start off with the coordinates, the usual xyz coordinates. We push them down the negative z-axis to make a new coordinate system sitting out the negative z-axis, and then we tilt it for the azimuth as the new local coordinate system. So sometimes that's an easier way to think about it. When you get more used to this, you can switch back and forth easily, but at first it can be very confusing. Okay, that's it for this presentation. Thank you very much.